This is Module 12, Section 7.1, about simplifying rational expressions. Let's talk about what a rational expression looks like. This is something that can be written in the form p over q, where both the p and the q are polynomials, and the q is not equal to 0. Now the reason for that is that if the q were equal to 0, since it's in the denominator, that would cause us to divide by 0, and division by 0 is undefined. Here are three examples of rational expressions. If we look at this first one on the left side, we have, for our numerator, 3x squared plus 2x minus 4. And notice that this is a polynomial. We have coefficients and different powers of x. In the denominator, we have 4x minus 5. For our second rational expression, we have 2y on the top, and the polynomial in the denominator is 4x plus 3xy minus 5. So notice that a polynomial can also include combinations of different variables. And last of all, we have 5x squared over 4. Notice that the 4 here still counts as a polynomial even though it's a constant. Remember, a constant is just a special form of a polynomial. The first thing we're going to do with rational expressions is to evaluate them. And when we talk about evaluating a rational expression for a particular value, what that means is that we're going to substitute our replacement value into the rational expression and then just simplify the result. Here's our first example. The expression that we want to evaluate is y minus 2 over negative 5 plus y, and our replacement value is negative 2. So what this means is that we're going to substitute negative 2 in place of the y every place that there's a y in this expression. What I'm going to do is rewrite the expression and put in parentheses every place that there was a y in the original expression. So now instead of y minus 2, we have a parentheses minus 2, and on the bottom we have negative 5 plus a set of parentheses. Now that tells me that I need to substitute my replacement value in where those parentheses are. Our replacement value was negative 2. So I'm going to write negative 2 in there and negative 2 in there. So I've got the substitution part done. Now I just need to simplify the result. And remember, when you're doing this, you have to think about order of operations, and that tells us that we have to work through everything in the numerator and through everything in the denominator first before we can do any kind of division or canceling between the numerator and the denominator. So first let's look at the numerator. We have negative 2 minus 2. That would give us negative 4. In the denominator we have negative 5 plus negative 2, which would give us negative 7. So now we've completely simplified our numerator and our denominator. And now we can look for any factors that the two have in common. And actually the only thing that these two have in common is that they're both negative. These negatives will cancel each other out. So we end up here with a positive 4/7. And that would be our final answer. Let's look at two more examples. So here we've got our rational expression that we're going to evaluate. And then right here is our replacement value we're going to use. So here we're going to use negative 3 in place of x for our replacement value. So again, I'm going to rewrite the rational expression just putting in parentheses wherever I see an x. So instead of x squared, I've got a parentheses with an exponent of 2. Then I have 5 times x, so I'm putting a parentheses there. And in the denominator, again, we have an x squared, so I have a parentheses with an exponent of 2 and then a plus 1. Now that tells me that wherever there's a set of parentheses, I need to go back and substitute in our replacement value of negative 3. Now the reason it makes such a difference in this case to use the parentheses, negative 3 squared is negative 3 times negative 3, which would give us a positive 9. So again, we're using the order of operations here, which tells us to do exponentiation first. We've done that in the numerator. Now we can actually go ahead and do this multiplication, the 5 times the negative 3. That gives us negative 15. Then we have the negative 2. And let's do the same thing in the denominator. So again, we have the negative 3 in parentheses squared, and that's going to give us a positive 9 plus 1. Now all we have left in the numerator is addition and subtraction, so we do that from left to right. 9 plus a negative 15 is negative 6. And all we have left in the denominator is the addition, 9 plus 1. So we can go ahead and do that and get 10. Now notice what we're not doing here, even though it's tempting to try and cancel out these two 9s, that's not following order of operations. We have to do all of our simplification in the numerator and all of our simplification in the denominator first before we can do any canceling. So one more step in the numerator, negative 6 minus 2 is negative 8. So we have negative 8 over 10. Now, if we have any factors in common between the numerator and denominator, we can cancel them. And since both 8 and 10 have a factor of 2, we can cancel out a 2. So that gives us 4 up here and 5 down here. And that gives us a final answer of negative 4/5. Let's do one more. In this one, our expression is x plus 4 over x minus 2. So again, I'm rewriting this using the parentheses. And now I can put in my replacement value of 4. And even though in this case it doesn't really make a difference to have this in parentheses, it's just a good habit to get into. That way you don't get confused by having a problem where you do have a negative replacement value. So on the top we have 4 plus 4, which is 8. In the denominator we have 4 minus 2, which is 2. And now that we've simplified each one of those separately, we can cancel out common factors. These have a common factor of 2. So if we cancel that, we get 4 on the top and a 1 on the bottom. And 4 over 1 we can just write in a simpler form as 4. Now let's look at this expression again. We have y minus 2 over negative 5 plus y. And think about what would happen if we tried to evaluate this for a replacement value of y equals 5. So let's just try this and see what happens. Now if we use our replacement value of 5 and simplify, on the top we have 5 minus 2, which is 3. On the bottom we have negative 5 plus 5, which gives us 0. Since we're dividing by 0, this gives us an expression that's undefined. So let's look at this. How do we know what values give us undefined rational expressions and which values don't? Something we need to be able to determine is when a rational expression is undefined, which replacement values give us something that's undefined. So the basic idea is that a rational expression is undefined when the denominator is equal to 0. It's okay if the numerator is equal to 0, because a rational expression with a numerator equal to 0 just gives us a value of 0. So here's another example. We're just going to evaluate the expression x squared minus 4 over x minus 1 for two different replacement values, x equals 1 and x equals 2. So if we start with the x equals 1, again, I'm just starting out by writing the expression with the parentheses put in. Now, if we're using x equals 1 as our replacement value, then we put a 1 in both of the parentheses. 1 squared is 1, so here we have 1 minus 4, and 1 minus 1 here is 0. So we don't even have to go any further with this. We can see that our denominator is 0, and that gives us an expression that's undefined. Now let's look at our other replacement value. So if we're using 2 for replacement value now, here we have 2 squared, which is 4. And in the denominator we have 2 minus 1, which is 1. In our numerator we have 4 minus 4, which gives us 0. In the denominator we have 1. Now this is the second case that we talked about up here. In this one the numerator is equal to 0, which is okay. That just gives us a value of 0. So for each of these rational expressions, let's see if we can find the numbers for which the expression is undefined. So what we're looking for is where is the denominator equal to 0? Now really the easiest way to think about that is to take our denominator and just set it equal to 0. So whatever expression we have in our denominator, we can take that, in this case it's x minus 2, and just make an equation out of it by setting that whole expression equal to 0. And then we can solve this one. In this case we're solving it for x. So if we solve this for x, we can do that by adding 2 to each side. So over here we just end up with x, and on the right side we end up with 2. So what we did by doing that is we found the value that makes our denominator equal to 0, which makes our expression undefined. So this tells us that our expression is undefined. If our replacement value is 2, so it's undefined for x equal to 2. Okay, let's try with this one. Now again, all we're going to do is take our whole denominator and set it equal to 0. Now to solve this for a, we would divide both sides by 4. Here the 4's end up canceling, so we have a equals 0 over 4, and again here, since we have a 0 on the top, that just gives us 0. So the solution for our equation is a equals 0, and that means that this expression is undefined when a is equal to 0. Okay, the last one here is a little bit more complicated, but again, we're taking our denominator and setting it equal to 0. This one we're going to solve for y, since that's our variable. And this one is going to be a little bit more complicated to solve just because it's a quadratic polynomial instead of just being a linear polynomial like the two up here were. Now the easiest way to solve this one is to factor it. If you notice that y squared and 5y have a y in common, so that would be our greatest common factor. If we factor that y out, then we have y times y minus 5. And remember that if we have our left side split up into factors and our right side equal to 0, then we can take each of our two factors and set them equal to 0. That's going to give us two different solutions for this equation. So from this first one we just get y equal to 0. From the second one we have y minus 5 equals 0. And we need to do one more step to solve this one, and that is to add 5 to both sides. So we end up with y equals 5. So here's one solution for our equation up here. Here's a second solution for our equation. So there are actually two places where our expression is undefined. So our expression is undefined for y equal to 0 and for y equal to 5. Now notice the one thing that we didn't do in any of these problems, we didn't look at the numerators at all. And if we're looking for where the rational expression is undefined, we don't need to look at the numerators. Those have absolutely nothing to do with where the rational expression is undefined. So the only thing that we're looking at here is the denominators. Now let's talk about simplifying rational expressions. And to simplify a rational expression means that we're going to write it in lowest terms, or you might have heard this called simplest form. What we're going to use for this is called the fundamental principle of rational expressions. And that just says that if p, q, and r are polynomials, and the q and the r are not zero, then if we have pr over qr, that's the same as p over q. All we're saying here is that if there is a factor in common between the numerator and the denominator, like the r is in this case, then we can cancel that out and just be left with the p over q. So what we're going to be looking for in these is factors that we can cancel. Here are a couple of examples, and notice that here our expression is already factored in both the numerator and the denominator. So what we're looking for is factors that are in common. And notice here we have the y minus 1 factor in both the numerator and the denominator. So all we're saying is that to simplify this, we can cancel those factors because they're in both places, and the simplified form of this expression would be just y plus 3 over y plus 5. Now let's look at this expression. Again, this is still a rational expression even though the top is a constant, because a constant is just a special type of polynomial. So the question is, what do the numerator and denominator have in common here as factors? Well, that would be the 2. Now be a little bit careful here, because remember, if you cancel out everything, if you cancel out every factor from either the numerator or the denominator, you do still have a 1 left. So we really still have a 1 in the numerator, and we're canceling the 2 out of the denominator, so we have an x left there. So this would be equal to 1 over x. So let's look at some steps for simplifying a rational expression. The first step that we need to do is completely factor both the numerator and the denominator. And the reason for doing this is that if you already have everything factored, then it won't be so tempting to cancel out things that are only terms. Once you have everything factored, then it's easier to identify what the factors are and if there are any factors in common, so that you're canceling out the appropriate things. So that's the first step. The second step then is to go ahead and cancel the common factors. And again, remember that you can only cancel factors. You can't cancel terms. Here's one example. A rational expression is 2x plus 16 over x squared plus 8x. So our first step is to factor. So in the numerator, if we're just looking at the greatest common factor between these two terms, it would be 2. So we're going to factor a 2 out of each of those two terms, and that gives us 2 times x plus 8. In the denominator, our greatest common factor would be x, because we have an x in both of those terms. So here, if we factor an x out, then we have x times x plus 8. Now both the numerator and denominator are completely factored now. And now we can look at the factors. So for example, in the numerator, 2 is one factor, x plus 8 is another factor. And in the denominator, x is one factor and x plus 8 is another factor. So we do have a factor in common between numerator and denominator, and that's the x plus 8. So our second step is to cancel. So I'm going to write this out again just to make it very clear what we're doing. And that is that we're canceling our common factors, which were x plus 8. And that leaves us with a 2 in the numerator and an x in the denominator. And that's all we can do. There are no more common factors that we can cancel. Let's do a few more examples of this. So again, our first step is to factor. And in the numerator for this one, we do have a greatest common factor of x because both of these terms have an x. So here we're doing our first step of factoring. So we have x, and if we factor that x out, then what we have left is x and minus 5. Now in the denominator here, we already have our two factors, so this has already been factored. We don't have to do anything else with our denominator. So now we're going to look at canceling since we have everything factored. So the factors that we have in common, we have an x minus 5 here and an x minus 5 here. So we're going to cancel those two. And that leaves us with an x on the top and an x plus 3 in the denominator. Now notice this is one place where it's really easy to slip up because you have to pay attention to whether you have factors or terms. In the denominator now, since we have a plus in between these two, each one of these is a term. So the x is a term and the 3 is a term. And that means that we cannot cancel the x here with the x up here because it's only a term. It's not a factor because it's not multiplied times something else. So this is our final answer. Okay, let's look at the second example. So first we're factoring. On the top there's nothing to be done. And on the bottom actually there's nothing to be done either. There's nothing that we can do to factor. And again, if we look at our denominator, we have two terms here. They're separated by a minus sign, which makes them terms instead of factors. And that means that we can't cancel either one of them. Even though it looks like maybe we should cancel this y with the y squared up here, we can't because it's only a term. So this one is already as simplified as it can get. Okay, last example. We have a squared plus 8a plus 15 on the top and a squared plus 9a plus 18 on the bottom. And both of these we're going to have to factor, and both of these are trinomials, so we're going to factor them, or try to factor them, into two binomials. And both of these are a little bit simpler trinomials to factor because the coefficient for the a squared in both cases is just 1. So here we know we're going to have an a for the first term in both binomials. And remember, we want two numbers that multiply to give us 15. And since our second sign here is a plus, that means we want to add them to get 8. Now the other thing we can do, you might have learned some different ways to decide where your signs go and where your numbers go. The way I like to do this is that I copy the first sign into my first binomial. So since that was a plus, then this becomes a plus. And then for the second sign, if this second sign is a plus, that means that they both have to be the same. So that would make them both pluses. And if you use this method, then when you find your two numbers, just put the biggest one in the first binomial and it will always work out. So if we think about what multiplies to 15 and adds to 8, this would be 5 and 3. Because 5 times 3 is 15 and 5 plus 3 is 8. So we'd have a plus 5 and a plus 3. Now in the denominator, again, we've got a trinomial to factor. So we've got a and a. Our first sign here is a plus, so we're going to make this first sign a plus. And since our second sign is plus, that means that these both have to be the same, and that makes this a plus also. So now we want two numbers that multiply to 18 and that add up to 9. So two numbers that would do this would be 6 and 3, because 6 times 3 is 18 and 6 plus 3 is 9. So we can put the 6 there and the 3 there. Now we've got both the numerator and denominator completely factored, and that means we're going to look for common factors now, and we do have a factor in common, and that would be the a plus 3. So we're going to cancel those two factors, and that leaves us with a plus 5 in the numerator and a plus 6 in the denominator. And again, be careful to not cancel terms. For example, here the a in both the numerator and the denominator is only a term because it's added to the 5 here and it's added to the 6 here. So we can't cancel those a's. Just like back here, you might have thought that we could cancel the a squared since we saw it in both places, but because of this plus here, that means that this a squared is a term. And the same thing with the plus here, that makes this a squared only a term and not a factor. And that means that we can't cancel it. Okay, now let's talk about expressions that are opposites. This is something that we see quite a bit in simplifying rational expressions. So if we talk about the opposite of an expression, it's just the product of -1 and that expression. So for example, the opposite of x minus 4 is found just by taking -1 times the quantity x minus 4. Now since we're taking it times the whole quantity, we have to use the distributive property. So we multiply the -1 times both the x and the -4, and that gives us -x plus 4. So it changes the sign of both of these. Now the tricky thing about this is that we can write it either in this order, or we could also write it as 4 minus x. So you might see it in both of these two forms. Now let's look at the opposite of -x minus y. And again, to get the opposite, we're just going to multiply by -1. We're distributing that to both of these terms. So -1 times -x would give us a positive x. -1 times -y would give us a positive y. So x plus y is the opposite of -x minus y. Okay, finally let's see how we use this in simplifying expressions. So if we're trying to simplify this expression, we'd start out by factoring. The top here is really already factored. And on the bottom we have a common factor of 2 that we can factor out, so that gives us 2 times z minus 6. Now here's where the idea of opposites come in, because if you look at these two, the 6 minus z and the z minus 6, these look a lot like up here where we had the x minus 4 and the 4 minus x. So if you see something like that, you might think that these two might be opposites. So let's rewrite this one as -z plus 6. And then if we rewrite it again, if we pull that -1 out to the front, like how we had here, then that would give us -1 times z minus 6. And we still have the z minus 6 in the denominator, both of these places. Now what that did for us is it gave us a common factor that we can cancel out. So by rewriting the 6 minus z as -1 times the opposite, then that allows us to cancel this. And that simplifies just down to -1/2. So that's something that you should really look for, especially when you have something like 4 minus x or 6 minus z. You can always rewrite that by sort of factoring out the -1 like we did here. Let's do a few more examples. So here we have -2x minus 2y. And again, we want to start out by factoring since we're trying to simplify. And notice that both of these have a factor of -2. So let's go ahead and factor out that -2. Now remember, when we do that, it's going to change the signs of both of these since we're factoring out a negative. So that's going to make this x plus y. On the bottom, there's no factoring to be done. So we have x plus y there. And now notice that here the x plus y, even though it's the only thing in the denominator, it does count as a factor. So we can cancel it with the x plus y factor that we have on the top. Now technically, when we cancel this out, we have a 1 left. So we end up with -2/1, which is just the same as -2. Now let's look at the second example. And here again, we have that form of the expression where we have the number first and then a subtraction. So let's go ahead right off the bat and rewrite this one as -1. So we're going to factor out the -1, which is going to turn this around and make it a minus 10. And if you need to go back to the last slide and see the steps of how we actually got to this, then go ahead and do that. Now on the bottom, we want to factor this also, and notice that we have a squared here and we have 100 here. Remember, 100 is the same as 10 squared. So this we could factor as the difference of squares. So that would give us a plus 10 and a minus 10. And notice now, since we rewrote our numerator, we do have the a minus 10 factor, which is in common between the two. So we can cancel that one out. We end up with -1 in the numerator and a plus 10 in the denominator. Okay, our final example here on the top, since we've got 4 different terms, we're going to use factoring by grouping. So remember, that means that we group the first 2 terms together, we group the second 2 terms together, and we factor out whatever they have in common. So between these first 2 terms, we have an x in common. So if we factor that out, then we have x times the quantity x minus y. And if we look at our second 2 terms, they both have a 5. So let's start out by factoring out a 5 and see what happens. So if we factor a 5 out of here, then we have a negative x, because that was a negative 5x, and a plus y. Okay, now let's look at the bottom at the same time. So these two have an x in common. If we factor that out, we'd have x times x minus 5. Now let's look at the numerator just a little bit more. Notice that our first quantity we have x minus y. Our second one we have negative x plus y. Now for factoring by grouping to work completely, these 2 factors have to be exactly the same. So the way we have it written right now, it won't work. But again, notice that we have x minus y and negative x plus y, and these 2 are opposites. That means that we could rewrite this second one as -1 times x minus y. And that would give us x minus y, which would match with this first one. So let's rewrite this a little bit. So we still have our plus 5 here, And then our negative x plus y we're rewriting as negative 1 times x minus y. And in the denominator we have x times x minus 5. Okay, so let's rewrite this one more time on the top. Let's just multiply the 5 times the negative 1, which gives us a negative 5. So we have negative 5 times x minus y. This might seem like the long way around, but I want you to see all of the steps to get from this down to where we have two factors that match. So now for our factoring by grouping, we have an x minus y in each place. So we're technically factoring that out, and what we have left from the first term is an x, and from the second term we have a negative 5. On the bottom we have x times x minus 5. So now we have a factor in common, which is the x minus 5. So to simplify this, we're going to cancel that out, and we're left with an x minus y in the numerator and an x in the denominator. And again, this is as far as we can go, because this x up here is a term. Because we have a subtraction after that, it's only a term, which means we can't cancel it. So there's nothing more that we can do with this one. This is the end of section 7.1. So now you can go ahead and start working on your homework problems.